Hey everyone, welcome to this explainer. Today, we're diving straight into the absolute backbone of our digital lives, decoding total DNS and DHCP. These are the unsung heroes of literally every network, quietly operating behind the scenes to make sure you can actually connect to the web and find what you're looking for. Without them, the modern internet simply wouldn't function. Here is our roadmap for today. We'll start by meeting DNS and DHCP, walk through the DHCP DORA process, and track the DNS resolution flow. Then we'll decode DNS record types, look at securing our infrastructure, and finally cover how to troubleshoot network failures. Section 1. Meet DNS and DHCP, the invisible infrastructure. First up, DHCP, or Dynamic Host Configuration Protocol. You know that magic moment when you connect your phone to a new Wi-Fi network and it just works? You don't have to manually type in some crazy string of numbers to get online? Well, that's DHCP right there. It seamlessly hands out your digital identity the second you join a network. It automates your IP address, your subnet mask, and your gateway, completely eliminating the headache of manual IP conflicts. And once you actually have that IP address, DNS steps in. It does the heavy lifting, translating website names into numbers that your machine can actually route to. I mean, we're great at remembering names like google.com, right? But computers, they only understand IP addresses like 8.8.8.8. So DNS basically acts as the internet's phone book. It's this massive, distributed, and highly hierarchical database that makes web browsing totally effortless for us. Moving right along to Section 2, DHCP, the DORA process. Getting on the grid. Let's look at the fascinating four-step communication dance that happens in mere milliseconds after you plug in a network cable. It's called DORA. First, discover. Your client device has no IP, so it basically shouts a broadcast to the entire local network saying, hey, are there any DHCP servers out there? Next is the offer. A server hears this and replies with a proposed IP address and a lease time. Then your client sends a request, broadcasting its acceptance of that specific offer. It does this as a broadcast, so if multiple servers made offers, they instantly know theirs were rejected and can take their IPs back. Finally, acknowledge. The server confirms the lease, and boom, you are officially on the grid. Now, here's a really cool feature to note. Option 82. In massive enterprise networks, DHCP needs to be pretty smart. Option 82 allows a network switch, acting as a relay agent, to actually inject information about the physical circuit into the DHCP request. This means admins can cleverly assign IPs based on exactly which physical switch port or VLAN you're plugged into. It is an absolute game changer for automatically provisioning things like VoIP phones versus guest laptops. Section 3. DNS, the resolution flow. Finding the destination. So now that our device is fully configured with an IP, how exactly does a single search cascade from your laptop all the way to the internet's root servers and back? Well, it starts when you type a URL. Your local machine, the stub resolver, checks its own cache. If it doesn't know the answer, it asks your ISP's recursive resolver to go find it. That resolver then queries one of the 13 global root name server clusters. Now, the root doesn't know the specific IP, but it refers the query to the top-level domain, or TLD name server. Think of the servers managing all .coms. The TLD then points to the authoritative name server for that specific domain. Finally, the authoritative server hands over the exact IP address. The resolver caches this answer based on its time to live, or TTL, and hands it right back to you. Magic, right? The absolutely crucial distinction to remember here is who does the actual legwork versus who holds the ultimate master record. Recursive DNS servers, they're your proxies. They are the detectives going out, iterating through the hierarchy, and asking all the questions on your behalf. Authoritative DNS servers, on the other hand, are the source of truth. They hold the actual zone data for a domain and provide definitive, direct answers marked with an AA flag, rather than just referring you elsewhere. Essentially, you run authoritative servers for your own domains, but you use recursive resolvers to actually browse the web. Section 4. Decoding DNS record types, the internet's phone book entries. Let's decode the specific types of entries held within those authoritative servers. Because honestly, it's way more than just simple names and numbers. The A record is your bread and butter, mapping a hostname to an IPv4 address. AAA does the exact same thing, but for modern IPv6 addresses. A CNAME is just an alias. It points a name to another name, not directly to an IP. MX tells the internet where to deliver email for your domain, complete with priority numbers. And every single zone starts with an SOA, or Start of Authority record, which holds crucial metadata like the serial number and refresh timers for the zone. Okay, quick interview tip. And this is a classic trap for junior engineers. You literally cannot put a CNAME at the very root of your domain, often called the zone apex. Why? Because a CNAME cannot coexist with other records at the same name. Since your root domain absolutely must have an SOA and NS records, placing a CNAME there will just break your entire zone. It's a mistake you definitely want to watch out for. Section 5. Securing DNS and DHCP. Protecting the infrastructure. We really need to protect these critical protocols from malicious actors, because if attackers compromise your DNS or DHCP, they literally control your network reality. To prevent attacks like cache poisoning, where an attacker redirects your users to a fake website, we use DNSSEC to create a chain of trust. Here's how it works. The Zone Signing Key, or ZSK, cryptographically signs all your standard records. The Key Signing Key, or KSK, signs that ZSK. A hash of that KSK is then stored securely as a DS record in your parent zone. This creates an unbreakable cryptographic chain that resolvers can validate all the way up to the hard-coded root trust anchor. If the maths doesn't check out, the query is dropped. Simple as that. Now, what about DHCP? Say an attacker launches a starvation attack, flooding your server with Discover packets using spoofed MAC addresses to completely exhaust your available IP pool, denying service to legitimate users. Our frontline defense here is DHCP snooping. It's a switch-level security feature that filters traffic. It marks trusted uplinks and outright blocks rogue DHCP server offers or starvation attempts coming from untrusted client ports. It stops the attack dead in its tracks. Section 6. Troubleshooting network failures. When things break down. Let's see how all this applies in the real world when the help desk phone actually starts ringing. You receive a ticket. Users can't browse the internet. This is the classic, vague scenario every engineer faces. So how do we logically isolate the root cause instead of just guessing? Instead of panicking, we follow a systematic flow. First, scope the issue. Is it one user, a whole team, wired or wireless? Next, do the classic ping test to 8.8.8.8. If this fails, stop troubleshooting DNS right there. You actually have a fundamental layer 3 routing issue. But if that IP ping works and pinging google.com fails, well, now you know for sure it's definitely DNS. From there, check local configs using the ipconfig command, do some manual queries with dig to verify your resolvers, and of course, verify your firewalls are actually allowing UDP and TCP port 53 to pass through. The biggest takeaway here, especially if you're sitting in an engineering interview, is to always frame your knowledge through practical, real-world execution. Interviewers want to know you've actually solved real problems. So use the STAR method. Explain the situation, the task at hand, the specific action you took using the tools we discussed today, and the final result. Understanding total DNS and DHCP is like understanding the nervous system of the digital world. And I'll leave you with this provocative thought. As our networks grow vastly more complex and heavily automated, who is truly in control? The network engineer, or these invisible protocols operating in the milliseconds behind the scenes? Keep exploring, and I'll catch you in the next explainer.